have our second talk of the afternoon. Mark is going to continue his course, and after that, we'll have coffee in the matrix, and then the problem session in this room.
All right. Well, thank you again. Thank you, Zaru said. Thank you for coming back. Aru mentioned that because she traveled sort of internationally, transatlantically, adjusting for time zones is a big thing. I also traveled from 2 hours away to 2 hour different time zone, which doesn't seem like as much, but it has its own challenges. I'm finding myself getting hungry at weird hours of the day, and then I sometimes get hangry and things like that. So if there are any, feel free to attribute any sort of, as Aru said, brain farts to that 2 hour time difference. I'm sure. So also there's a beautiful reciprocity between Aru and my talk, as many of the figures you'll see today were finished during Aru's talk. So as she's writing her, lecture notes, I'm glad that I was able to return the favor. So the first lecture, we didn't quite get as far as I wanted to. The first lecture, we sort of saw broken surface diagrams. We saw this family of ribbon 2 knots. And I will mention right now that a lot of the, if you worked on the problems, you saw that there's some relations between ordinary or classical ribbon knots and ribbon 2 knots. Essentially, a lot of the ways that you might characterize a classical ribbon knot, the same thing is true for a ribbon 2 knot. So it gives kind of a really nice natural generalization of these things. I did want to define a few other classes of examples of 2 knots. Namely spun knots, twist spun knots, and roll spun knots. And these are sort of part of a larger family of deformed spun knots. So let's start off. I'm gonna ignore this for now. This was I was gonna talk about that chord diagram discussion we had and tie up some loose ends from last, but I'll maybe jump into it. I meant to talk about that at the beginning, but I can talk about this later if anyone cares. So the idea behind sort of these constructions is we take a classical knot and we want to somehow promote it to a 2 knot. So start off with sort of your favorite knot. I'm going to denote sort of knots in S3 as J because I'm already using K for my 2 knots. And essentially what I can do is I can sort of take a little neighborhood of a point on my knot. And if I remove this neighborhood, then what's left over is a copy of B3 with a tangle inside of it. Okay. So if I remove that little neighborhood, I get just another copy of B3 with a tangle inside. And instead of thinking of this as B3, if I want, I can sort of remove a point and think of it. I think I have a picture in my slides of this. I can instead sort of if I, don't care about compactness or anything, I can think of this as being a copy of the upper half 3 space with a tangle embedded in it. And what I can do is, this is going to be sort of a cartoon or a schematic, but I can sort of imagine taking that copy of the upper half 3 space and sort of rotating it around this axis. Okay. So on the right, we're going to see sort of this rotation action. And as I sort of follow it around, I can sort of see where this knot sort of traces out. It's going to trace out a family of tangles, I should say. And that family of tangles taken together will be a 2 knot. Okay. So we call this a spun knot. In particular, this is the spin of a trefoil. Okay. Any questions there? Oh, I should say I saw some people taking pictures. I will upload all these figures to the Google Drive folder that I created for the problem. So yeah, and I'll make these available to you coming up. So now there's ways to sort of, this gives you a nice family of knots, but it is sort of a somewhat limited family. And we can sort of enhance this construction by, as we're doing this spinning picture, by sort of moving the tangle around in certain ways. And so there's kind of a really nice way to think of this, which is I mean, this picture here, or this description of spun knots is kind of, not too bad to deal with, but when, I always have trouble thinking of roll spun knots, like visualizing that. So I'm gonna kind of frame it in a slightly different way to sort of set up the roll spins a little bit easier. So the first thing to know is if I take a classical knot, if I take the connect sum of J with its mirror, so that's going to be sort of a picture like this. Wow. Actually, I have a picture. I did all the work to put the pictures on here, so I should use them, okay? So if I take J, connect sum its mirror, I get a picture like this. And it's sort of a nice fact that J connect sum its mirror is always going to be slice, and in fact, it's always going to be ribbon. And the way that you construct a ribbon disk for this is you sort of just imagine sort of cutting my connect sum in half with an axis, and then sort of taking half of this picture, sort of dipping it down into B4, and sort of using the trace of that tangle to give you a ribbon disk, much in the same way we just did the spinning construction. This is essentially exactly what's happening here. Okay, so this gives us a nice ribbon disk that is bounded by this J connect sum J mirror. And what we're going to do is we're going to kind of build the twist spin and the roll spin by sort of building a cobordism between, sort of a nice cobordism, and then capping it off with 2 copies of this disk. Okay, so here's sort of our picture. We start off with our J connect sum mirror that lives inside of S3, but I'm basically just going to hit everything, multiply everything by an interval. Okay. So that gives us this product here, this product cobordism. So it's a nice standard knot. Now, if I'm going to call this C. Oh, okay. I'm going to call that C. And if all I care about is recovering the spun knot, what I can do is I can take this, I can take this. I can take this J connect sum mirror. What did I do wrong there? Oh, I connected it wrong. Okay, I can take this, I called this D sub J here. I can just cap off this product cobordism with 2 copies of D sub J, okay, of this nice ribbon disk that I just built. And I think I need to view full screen. Or maybe not. I just need to get rid of that menu bar. Okay. So capping this together, this just gives me the spun knot that I described before, and hopefully you can kind of see why this is. We're sort of spinning it, if you think of sort of this middle line here as being the axis, you're really just kind of spinning this knot around, doing a full turn like that, okay? Now, of course, spun knots, I mentioned we want to do some more complicated constructions. So the first thing we can do is we can imagine, instead of starting with this cobordism C, we can sort of, as we go up the cobordism, we can take one of these 2 factors here in our connect sum and rotate it around, kind of spin it around in this direction. Okay, so I can kind of spin this thing n times as I go from bottom to top. Once I've done that, I can then cap off with my 2 ribbon disks, and this gives me what's called the N twist spun knot, where J is the knot. So that's one way we can sort of enhance this. The other way is we could sort of imagine taking this knot here, this connect summand, and as we're going up, we can imagine sort of taking this connect summand and moving it along the knot, okay? And sort of having it travel along the length of the knot and then back to its starting position. And then we can repeat that a total of m times if we want. And by doing that, capping that off, we get the roll spun knot. Okay, now this picture is like not the standard picture you show, but for me, the roll spun construction always like confuses me what's really, if you look at like Fox's picture, I'm never really sure what's going on. This sort of makes it a little bit more, at least obvious to me. And I have a much nicer picture that I stole from Patrick and Hannah's paper, where on the left, they're essentially doing this roll spun construction. So you can see this little copy of the knot is just going to travel around the bigger knot and back to its starting position. On the right, you have the cobordism that gives you the twist spin by sort of just spinning the knot as you go up. Okay. So I'll pause there for any questions or comments.
I think process for spin is not real. Just,
Oh, isn't it?
I mean, that's what Maggie told me.
Oh, okay. Well, I believe
But
you.
I
believe Maggie,
I
so-
don't remember my memory, so I'm not sure.
Okay, yeah, so maybe Fox's is a little bit, is actually different, so.
I think
This is like
more like a little
Litherland, yeah, yeah. Other comments? Also, I find this easier than Litherland's to visualize, so. So Litherland's construction is very nice, yeah, Daniel.
Are these two operations commutative at all, or probably not?
they're committed to.
Yeah,
They are.
yeah. Yeah, and they're not, yeah, like they are different, like there are knots that, what is like the 2 twist spun trefoil is not a roll spin or something. There are examples where you have things that are one but are not the other. They do sort of give you genuinely different things, so.
Wait, what is commutative?
So if you do a twist and a roll, that's the same as a roll and a twist. So
Are you like concatenating the coordinates, or are you doing both operations simultaneously?
So you could construct this. So yeah, you can construct this by concatenating the coordinates, yeah.
And you're
And
saying it doesn't matter what order.
Yeah. Yeah.
Sure.
yeah, so like the M roll N twist J is equal to the N twist M roll of the same knot. Yeah. Other questions or comments? No? Okay. So this is kind of the other like standard family of 2 knots that you'll see when you sort of first look at knotted surfaces and 2 knots in particular. And so some of the homework questions or the problem session questions that I posted or that I gave you earlier involve this. So now that we've seen this, you can go back and do some of those if you didn't attempt them already. All right, I should keep an eye on my time here, or I'll run into trouble. Okay, so we've seen now broken surface diagrams, but I always find sort of broken surface diagrams are not the easiest way. I apologize if any of you really love broken surface diagrams. I have a hard time kind of drawing them, and that's why in the homework question or the problem session question, I said, hey, can you like think about how to draw it, but don't actually try and draw it because they can be a little hard to draw. So we'd like to have sort of, I guess, more convenient descriptive technology or ways to describe these things. And so that'll kind of lead us into like motion pictures and banded unlinked diagrams. So Aru sort of talked about these motion pictures. So I'm going to just sort of review some of the things she talked about and kind of set them up in a way that'll sort of lead into banded unlinked diagrams. Let's erase this. Okay, so for this part of the talk, at least, I'm gonna think of my knotted surfaces as living inside of R4. It's just a little bit more convenient, and I'm gonna think of R4 sort of as being given a product decomposition as just R3 cross R. So I've got some sort of distinguished coordinate, which I'm going to think of as my height function. Okay. So essentially what we want to do is we want to describe our knotted surface K by describing a sequence of stills where I'm going to denote by K sub T just what I get when I intersect K with R3 cross a time T. Okay. So I'm essentially just going to take time slices like Aru did. And in this picture, when I do that, I get a bunch of, for some choice of T or for some, assume that my surface is positioned like this. What I'm going to do is I'm going to get a family of intersections. And somehow by recording these intersections, I'm recording all of the information that you need to recover the surface entirely. Okay. Now, it turns out that it's actually a little bit complicated. You know, you have to sort of assume that there's not some isotopies going on in between, which might mess things up a little bit. But by sort of taking a fine enough sequence of cross sections, we can kind of get all the information we need to recover our surface. And sort of in between each of these stills, there's sort of only simple things are going on. Okay. So for example, between K0 and K1, we start with the empty set because our surface doesn't intersect this height. And when we pass to K1, what happens is we see a minimal point of our surface, and then we just get an unknotted component. And then between K1 and K2, we have another local min, so we get another unknotted component showing up. Between K2 and K3, we have a saddle point, and then sort of, and so on. We have a saddle point between K3 and K4, then a local max and a local max going sort of up that level there, okay? And so by sort of recording sort of a frequent enough time slices, we're able to sort of completely describe our surface, okay? Any questions there? Maybe I'll just show you. Oh yeah, there was a question.
That there's like, if you didn't have the picture on the left, how do you know that there's a saddle and not like capping off one of your components to get just like an unknotted S2 on the side when you say go from K2 to K3?
Oh yeah, how do you know that you don't just cap that off? So that's the problem, is that there does need to be a little bit more information here. And so we're gonna, when we talk about banded unlinked diagrams, we're gonna sort of capture everything that you need. But yeah, you would somehow need to like denote that. And sometimes people will denote it by like, they'll denote these things by graphs, and there'll be a certain type of vertex, or there's ways to do that. But yeah, you're right. You definitely need a little bit more information. Other questions or comments? And there is like, you do need to sort of make sure, because you know, you can imagine sort of like maybe between here and here, this thing sort of flips. Well, that's going to give you a different surface. You're going to get, you know, like you, or in this case, not, but it could give you a different surface if you're not sort of careful and you're allowing your components to move around in between stills. So you kind of want to, this is not the perfect method. We want to enhance this a little bit. So sort of what happens then is the only real things that we see going on between the stills are going to be sort of things like this, okay? So if you pass a local max, well, what does that look like? Well, it looks like a component sort of just vanishes, you know, an unknotted component that's unlinked from the rest of the diagram just sort of vanishes into thin air. If you pass a saddle point, you get a situation like this where two strings that are sort of close to each other recombine in this way. A local min looks like this, where, you know, at first you have nothing, and then an unknotted, unlinked component shows up. And then the last thing that can happen is when you're sort of traveling like this, you can have isotopies of your diagram take place, and that just sort of corresponds to like a sheet of the surface that like doesn't look like a product entirely, like it maybe wiggles at the bottom and doesn't wiggle at the top. That's going to sort of correspond to an isotopy of your components in your cross section. Okay. So that sort of like captures everything that can go on. And so now maybe let's look at like an example, a proper example of a diagram that's not just sort of, you know, not just sort of a sphere in 3 space. So this is an example of a knotted surface. And I should have flipped it or something, or reflected it maybe, so that we're reading from left to right on the top. But anyways, we're starting at the top right corner. And so we see sort of the first thing we see is we see 2 local min appear. Then what happens is we have an isotopy of our 2 components. So I've tried to draw enough stills so you can kind of see what happens. The red component kind of goes up, links through the blue component, then comes back through itself, and then it kind of goes back to the red component. I don't know how to like, so we get sort of to this point where all we've really done is the red component is kind of moved around, okay? Now here, the red component and the blue component become close, and we're gonna see a saddle point appear right there. And after the saddle point, now we don't have a red and blue component. They have recombined to form a purple component. And now, so now we have this properly knotted thing. And what we're going to see is we're going to see another saddle point occurs sort of right in the same place where that first saddle point appeared. And what that does is it then separates us back into two components, a red and a blue. And what's going to happen is this red component is just going to sort of travel back through via ambient isotopy back to sort of our starting position. And then they're going to get capped off with local mins. Okay. So any questions on how to like interpret this kind of picture here? Or complaints or anything? Yeah.
Is this just the normal?
Oh, this is this just a knotted? It is a, let's see, so it's, yeah. Yeah, so this is just a ribbon knot. It's going to be a ribbon knot with two spheres, and I'd have to think about it a bit to make sure it's unknotted, but I think it is.
No, it's a
I think it is not it.
Is it knotted? Is this spun trefoil?
Yeah.
Okay. What's that? Oh, okay. I can't see that on the fly. So I believe it's the spun. I believe whatever everyone said. So yeah. Same thing Aru said. I believe you. Yeah.
Again, it's a spun triple.
It's spun triple. Okay. Yeah, spun triple. Okay. All right. So okay. Now the complaint. Any other questions or comments?
Maybe some. Well, maybe not.
Oh, maybe not spun trefoil? Okay. I definitely agree with maybe spun trefoil, maybe not. That I will save money on. So, and there's no way that I could, yeah. Yeah. Okay. So I have a complaint. My complaint is that this is a sort of terrible, like it's just sort of an inefficient way to draw diagrams because you're just sort of drawing a ton of diagrams to do stuff. So what we'd like to do is we'd like to sort of like compactify this or sort of compress this down to as few of pictures as we need to, okay? So the first thing we can do to sort of simplify our lives a little bit is we can flatten our critical points, okay? So we have a maximal point, we have a saddle point, we have a min point. We can sort of, squash the top of that max point down. We can sort of squash the bottom of that min point down and flatten them out. Okay, so squashing the maximal point gives me a picture like this. And I'm going to call that disk up top there. I'm going to imagine that disk lies entirely at a given height, a specific height. So I'm going to call that a maximal disk for obvious reasons. I can also sort of flatten the saddle point down a bit. And essentially what I'm doing is I'm kind of like, I don't know, creasing it or flattening out a little region in the middle of that saddle point. It's kind of maybe a little hard to see, but I've kind of just like flattened this out. So it's not a proper saddle point anymore. Now it's a family of sort of critical points all at the same height. I'm going to call that a saddle band. And then with this local min, I can sort of squash it and turn it into a minimal disk. And again, I think of that minimal disk as sort of that entire disk is living at the same height in my knotted surface. Okay. So let's see how much better we've made our lives. Well, this was our diagram we started with. We want to sort of like get rid of as many pictures as possible. It turns out that we're not able to like simplify it too much. We were able to sort of get rid of like the dot appearing and turning into a thing. We can sort of just replace that with, well, actually, honestly, no, we didn't really even do that because I still cut off it. So anyways, we haven't made our lives any better, is what I'm saying. Okay. So notice I replaced just sort of these minimal and maximal points with now just disks. And instead of sort of drawing these things as saddle points, I'm just replacing them with a band. So I haven't really simplified our situation at all. Okay. But with a little bit of work, I can sort of make our lives a little bit better. Okay. But before I do that, let me make a definition. Okay. All right. So here's going to be mostly notation. So let L be a link in S3 or R3. And let's let B be a family of bands attached to L. Okay. Then I'm going to let L sub B denotes the result of performing band surgery. No, that's not how you spell it. Performing band surgery on L along B. Okay, so what do I mean by band surgery? Well, I've got my link L here, and I've got some band that's attached to L, which I'll call B. Performing band surgery is really just, I'm gonna, remove part of my link where the band is attached, and then glue in sort of the other part of the boundary of my band. Okay. That's what our band surgery looks like. And I'm going to denote this by L sub B. Okay. So let's see. So now kind of looking at this picture here, I can kind of think about this picture now in terms of band surgeries. Okay. So really up here, we have sort of two unknots up here. Okay. And they isotope themselves around until we get to a height where there's a band surgery. And now the difference between this unlink and this knot here is that we perform band surgery along this purple band. Okay. And then we have another band up here. We perform band surgery again. And now we have an unlink again, which we can then cap off. Okay. So, so we can kind of just rephrase this whole picture in terms of band surgeries. And we can, yeah. So questions there on the band surgeries or anything? Okay. So if you look at this, I think of sort of this picture, like there's a lot of heavy lifting being done by ambient isotopy, like moving the components around. A lot of the rearrangement is just done in terms of moving components around. But suppose that ambient isotopy, I'm lazy. I don't like to do ambient isotopies when I don't have to. So imagine we sort of take this part here, this strand here, and we sort of pull it back through here, all the way back to this point here. And while we're doing that, we're stretching the band along with it. Okay, so instead of a bunch of ambient isotopy happening, we're going to kind of undo all the ambient isotopy that we needed to do. But when we're doing that, we're stretching the band along with the reverse of the ambient isotopy. So essentially what we're doing now is we are, we're sort of like replacing ambient isotopy with a more complicated band. And so now my picture starts off with my minimal disks. I get two components, and now I'm not going to move the components around at all. I'm just going to make a more complicated band connecting the red and the blue. And if you go back to that first picture, that's exactly what we did there. When I do my band surgery, I get this picture. And now I can do band surgery again on my second band. But now I end up with this picture here, and I'm kind of stuck. I either have to do an ambient isotopy to basically undo it or cap everything off, or I could just say, well, hey, as long as I think of my disks as being stretchy enough, I could sort of just like get rid of all that ambient isotopy and just think of my disks as sort of have sort of stretched themselves out along with the ambient isotopy. Does that kind of make sense? So now essentially what I'm doing is instead of just having a nice little disk that I can cap off in the obvious way, I have to think a little bit more clearly about how to cap off. It's still a two-component unlink, so we know that it can be capped off with two disks, but those disks are a little less obvious to see when I haven't straightened my unlink out, okay? Any questions or concerns there? Complaints? No? Okay. Let's see. So this has kind of made our lives better, but unfortunately, like I don't like to draw really weird discs. Do I have to draw really weird discs? No, because of question 5, right? And so we'll come back to this in a second, but we did have in that first problem section, there was a problem that essentially says families of disks that cap off these unlinks are unique up to isotopy if you allow yourself to sort of dip into the 4-ball a little bit. So I'll make that a little bit more precise in a second. But let me just state sort of a lemma now. Have a good marker. There we go. Okay. So here's a lemma. So given a knotted surface K, we can always rearrange the heights of the critical points as follows. Okay, so we can always sort of interchange the heights of 2 max or min points. Okay, we can always move a band up past a minimal point. So if there's a minimal point above a band, we can move the band above the min point. If there's a maximal point above a band, or sorry, if there's a maximal point below a band, we can move a band down. So maybe I'll just say move a band above or below a min point or a max point. I think I said that right. So if I have a band that is below a min point, I can move it above that minimal point. If I have a band that is above a maximal point, I can move it below. Does that make sense? Maybe that was really confusing. So say I have a band here and I have some local min here, I can always move my band down. Okay, and that's assuming that it's connected somewhere to some other components in our picture. And then the third thing we can always do is we can interchange the heights of 2 bands. Okay. So let's look at this in terms of pictures. So if I have 2 maximal points, I can always sort of move the lower one above the higher one. If I have a pair of saddle bands, I can sort of interchange their height. In this way, I can move one down, the other up to interchange their height. Now, do you have any complaints on that? Can I always do that in the way that I've drawn it?
They're nested.
Nested or
Maybe I'm not thinking the right word, but like right now, they can sort of happen in the disjoint.
yeah, that's the problem, right? Is that this picture is like vastly simplifying what could happen, okay? And this issue of like when these things are not kind of so disjoint, can we really still switch them? That is going to lead to that's going to lead to a little bit of ambiguity that we need to resolve. So that if you're complaining about that, rest assured it will be addressed, but in a moment's time. So just urge patience and your continued cooperation with this. I should say I spent way too much time drawing that picture. So I would like to linger on it just a moment. I did that on the plane and I spent like a good chunk of like, it was probably like all of Colorado and Kansas. And I don't even know what's after that, but like, no, I probably didn't even go there. Anyway, the lady sitting next to me, like, I think she really wanted to ask me like what in the world this all was, but I spent way too much time. I don't know. The quality of the other figures definitely suffered as a result of like my sort of attention to this figure. But anyway, And it's not even perfect, but I need to just let it go and just be happy with it. So, oh, thank you. So, okay. So now that we've looked at it long enough, what we're going to do is we're going to, again, keep in mind that sort of this picture is sort of deceptively simple, okay? And there is some ambiguity that we're going to run into, but we'll deal with it in a moment. And because we can do this, because we can kind of rearrange heights in this way, as sort of a simple, I guess, corollary to this is we can always arrange that our max points live in, say, R3 cross 1. Our saddle points live in R3 cross 0, and our min points live in R3 cross, say, -1. Okay, so I mean, you can pick any 3 heights that you want, and you can always sort of arrange your maximal points live at the tallest, at the top one. Your saddle points live at the middle one, middle height, and your min points live in the middle. And because of that, we can always sort of arrange our diagram to look something like this. Okay. So we've got at height -1, we've got our minimal disks. At height +1, we've got our maximal disks. And then at height 0, we've got our bands. And so really all of the interesting stuff that's happening to our surface is now happening at those 3 discrete time slices, okay? And so as we're sort of traveling through here, we start off with an unlink, okay? Then we get a family of bands. We perform band surgery. And as long as the result of our band surgery is another unlink, it can then be capped off sort of in the way you see here, okay, in a unique way. So let's just make a comment here then. Or any question on this picture?
How long did it take to draw?
Not so long. What's that? Oh, you're here. I thought you'd gone off to do your typing or something. Okay, you are listening. That's wonderful. She promised she'd listen, and she did. So thank you.
My work here is done.
Yes. Slip out while my back is turned. You can do whatever now. Okay. So essentially, all of the interesting information is contained in this middle time slice, which we're going to call K0. All right. And in fact, what we'd like to be able to do is we'd like to just, if really all the important information is contained here, we'd like to be able to throw away every other piece of information. And in fact, we can do that. Okay. So by the earlier exercise, the max and the min disks are uniquely determined by L and by band surgery along L. And so because of that, we really don't even have to record the disks. It's enough to just record the unlink that appears after the minimal disks, as well as the location of the bands, and all the other sort of information is sort of uniquely determined. Now remember, the exercise basically says that that family of maximal disks is going to be uniquely determined, but up to isotopy rel boundary, but you may have to sort of push it. You may have to sort of push them into the 4-ball a little bit, okay, to sort of see that they're isotopic. So sort of you can draw them in different ways, potentially inside of 3-dimensional space. But if you're allowing yourself to sort of dip into the 4-ball, you can sort of see that they're isotopic. So this gives us then the definition of a banded unlinked diagram. I think I'm there. I stop at 4, I think, right? 4? Okay, I think that's perfect. So, yeah, let's define this. I have chalk in my hand and no chalk brush, so I'm gonna reuse the chalkboard here. So, so here's our definition. Then an unlinked diagram of K is a pair L comma B, where again L is an unlink. Well, let's say L is an unlink. B is a family of bands. And L sub B is an unlink. Okay, so not only is L an unlink, but when we perform surgery along these bands, we get another unlink. And from a banded unlink diagram, kind of in the way we've set it up, given a banded unlink diagram, this determines a surface, which I'm going to denote sigma, sigma LB, which is going to be isotopic to the thing you started with. Okay, so essentially, I'm kind of skipping maybe a step here or two, but the idea is that if you record that middle section where you've got an unlink in blue and you've got a family of bands in red, that's enough information to then completely reconstruct a surface, and that surface is going to be sort of the thing you start with. So any questions there? Yeah.
Actually, you need a slice this. A slice, not.
Yes. However, I think uniqueness is then a bit of an issue, right? Because if it's you know, you could imagine sort of different slice discs that cap off the same knot. And so if you yeah, I mean, this construction could be done with slice knots, but then you kind of lose the ability, I think, to record everything in a single still. So.
Know whether there are any slice knots other than sort of uniquely bound?
I don't know. I'd have to defer to someone else on that. Slice knots that bound unique slice disks. Does anyone know?
No, it's not possible because you're always connected some knotted tooth.
Oh yeah. That's the yeah. You could always connect some on any knotted tooth. Yeah. That's the way to do it.
Yeah, so our question would be like, can you make this with single?
Yeah, I guess you could say, like, is there a one that bounds a unique disk that can't be split up? Yeah, up to like connect some ends, probably. Yeah.
Just to make sure I'm reading the definition correctly here, like, I mean, you're saying that this looks to me almost like you're saying that any banded unlinked diagram is isotopic to K, but you're saying you're specifying like the definition is that these bands with these links are such that you get something isotopic.
Yeah, so I kind of, in the interest of time, I compressed two definitions into one, and I didn't actually parse it correctly. So you're right, like the way that I phrase this is terrible. Essentially, a banded unlinked diagram, ignoring the K part, is just a pair like this, where L is an unlinked, B is bands, and L surge of B is another unlink. From that, you can construct a surface, which we're calling sigma L comma B. And the point is that if you start with a knotted surface and you position it in this way so that all the bands are sort of at the same height, then that middle cross section is a banded unlink. And that banded unlink, if you sort of follow this construction through to get a surface, should be isotopic to the original thing you started with. So I did combine some definitions and not in a understandable way.
And then I just have one other question.
Yeah.
Is there ever like, do you ever want, or is it like for the LB to have the same number of components as L? Like, is that ever?
Yeah, if LB has the same number, it doesn't have to be.
It
Yeah.
depends on the changes, the surface that you.
Well,
Aren't we
so
talking about a sphere right now?
oh yeah. So if you're so So these can handle surfaces of any genus and non-orientable surfaces.
Yeah.
So are you saying the number of bands matches the number of unlinked components,
No, like
or
link after you do all the band sums, does it have to be the same number of components as the original link?
no? Because you could have sort of this situation where you have just an unknotted component and do a single band that's going to give you one minimal point, two maximal points, and a band. Yeah. So yeah, they don't have to be the same before and after number of components. Yeah. Okay, so yeah, so this is a banded. So the idea is that if you have a banded unlinked diagram, you can complete it to a surface, and I think I've kind of illustrated this, but here's just another picture of that. I think of my banded unlinked diagram as living in S3. I can cap off the unlinked components below using sort of disks, and then I can cap off the components above, which are again going to be unlinked, but might be sort of more messy, with another family of disks that is unique up to isotopy in V4. Okay. All right. So let's talk just a little bit. Maybe the last thing I'll do is I'll kind of finish this off, and I can come back to this, but I want to get back to that question of ambiguity. When I'm pushing my bands down to the same height, there are some issues that can arise. So in this picture here, I've got two bands, and if I push the one that's further to the right down, notice it's going to land smack dab on the other band. Okay. Now that's a problem. We don't want our bands to be attached to other bands. We want them to be attached to unlinked components. So I have a choice here. And what I can do is I can kind of push my band to the right a little bit, and I can get it out of the way. And so therefore, when I push it down, or when I push it to the left, it's going to land on the unlinked component and not on the other band. Okay. So we always want to make sure our bands are attached to linked components and not other bands. But what's the problem with that?
Push the other.
Yeah, I pushed it out this way. I could have actually pushed it along the band all the way down, and that would have given me a different banded unlinked diagram for the same surface. Okay. But it turns out that these two banded unlinks are related by something called a band slide. In fact, these are actually two band slides. Okay. And or I could have sort of slid one component this way and the other, one endpoint this way and the other endpoint that way, and I would have got a second band that's kind of tangled up along the first band. That would be sort of another representation of the same surface as the banded unlinked diagram. So although these two banded unlinked diagrams look different, they're related by a pair of band slides, and I'll show you a picture of a band slide in a second. But essentially, you can think of a band slide as basically taking one endpoint of a band and sort of sliding it along on the side of another band until it gets to the next link component. Okay. So if I do that with this endpoint, travel along, and I do that with this endpoint and travel along, you can see that these two band slides are going to give me this picture here. Okay. So that's one sort of little bit of ambiguity. Our pictures are only defined up to band slides. The other bit of ambiguity is maybe when I push my band down, instead of its endpoints landing on another band, maybe sort of the two bands intersect along the interior of one of them. So maybe I push one of my bands down and it sort of lands smack dab in the middle of another band. Well, what can I do here? Yeah, I can kind of push it to I can kind of push it to one side, but I could also have pushed it to the other side just as easily. And so in sort of obtaining this banded unlinked diagram, I may have to make choices where I'm sort of this is what's called a band swim. Okay. And I think of it as I think of sort of this middle band as being a river, and the other band can kind of enter that river on one of the endpoints, swim right across it, and then get out of the river on the other side. Maybe it's not a river, maybe it's more of a lake. Like it looks like a river, but if you were to go swimming in a river, you are not swimming. Do you know what I mean? Like you're not getting in at the start of the river and then swimming. You're kind of swimming more across. Yeah, I guess these are the banks of the river. Yeah, okay, those are the banks of the river. I understand the nomenclature now. Good. Yeah, there maybe maybe the name isn't perfect, but so essentially this is sort of all the ambiguity that can happen in a banded unlinked diagram. So this is was a theorem that was sort of originally conjectured, I think, by Yoshikawa, then originally proved by Swenton, and then Curtin and Curlin gave a different proof. But essentially, if I have two banded unlinked diagrams whose resulting surfaces are isotopic, then those two banded unlinked diagrams can be related by a sequence of ambient isotopy in S3 together with these three moves. Okay, so together with ambient isotopy, these, I guess, four moves are enough to sort of capture isotopies between surfaces described as banded unlinks. Okay, so I kind of described where the slides come from. This is sort of a band slide where we sort of take one end of the band, slide it along the other. This is our band swim, which we now have a nice visual interpretation of. The cap and cup move are sort of just Morse moves, where a cap move is like where you take sort of a local max with a saddle point that cancel each other out, and you sort of just like squish them down. And a cup move is basically a cap move upside down. Okay, so yeah, so when describing surfaces via banded unlinks, these are like the only moves you need to sort of get between any two representations. So I will talk a little bit about the proof of this. I'm going to essentially set things up in an arbitrary form manifold next class. And I'll talk about the proof there. I think the proof there is a little bit more, the proof there requires a little bit more careful thinking about how to flow things down along a Morse function. So I'll talk about the proof next time a little bit, so tomorrow. Any questions? I'm over time by 3 minutes, so I'll wrap up there. Yeah.
Can you go back to the bands? Oh, I guess this is fine. Do you see how it links with your unlink?
Yeah.
Then you have a choice there, like which part goes out.
Oh, like which part goes over and which part goes under? Well, I think maybe it's a little bit more clear with this picture here. Because I'm sort of entering the band from the top, it sort of has to link the unlink in the way that's shown on the left or on the right when you push it off. Like if I could,
Okay, yeah.
oh, is that okay?
Hang on a minute.
Okay, all right. I promise you the picture I was about to draw would not have finished this. We'll leave it there. Probably confused anyone who thought they were convinced.
Did you have a picture of the slide, like a similar thing earlier?
Oh, I have sort of this here is sort of really two slides, two band slides, one along sort of either endpoint. I do this is sort of the sort of the picture of a band slide where you sort of take one endpoint of a band and you really just move it along the edge of another band. Yeah. So, yeah. Of course, they can look a lot more ugly, especially when you start adding twists to your bands, because once you start adding twists, you're doing band slides then sort of adds more twists. So the bands are sliding. All right. Well, I'll end there. I'm over time already. So thank you. So then the problem section probably start. Oh no, it's coffee, right?
Yeah.
Okay.
Coffee and the problem section.